wanted to bring in some interesting concepts that it's almost the sort of things that we wish a developer knew when we come to run their microservice on Kubernetes. I actually work for a medium-sized Kubernetes consultant as a Kubernetes and scalability specialist. And we run a lot of services that, much like Praveen showed there with Orleans-based services, or maybe .NET or maybe Python, and they all share a lot of common traits. And what we like to do is have the developers not re-implement things that are already implemented as part of Kubernetes. I mentioned Kubernetes. We can really generalize this to any orchestrator, but I think, Orleans used to have its own sort of orchestration layer, and now it leverages Kubernetes. Service Fabric was touted by Microsoft for a long time as being the orchestration platform of choice. I think that's largely gone away now. I don't even think Microsoft would stand by their own advice to use, to sort of consider Service Fabric in the same vein. So really, Kubernetes is one to all intents and purposes. I've been using it an awful long time. I wouldn't necessarily count myself as an expert, but probably, I do advise on sort of large and small Kubernetes deployments. When we talk about a microservice, we're talking about something like this, which is essentially a service running under an orchestrator. Maybe it's reading something from a queue, maybe it's calling an HTTP service. And this is typical of what we see as services running on Kubernetes. So they do a relatively small function. They maybe host an HTTP endpoint, and maybe they push messages onto a queue. Maybe they host an HTTP endpoint and they store something away in a database. Maybe they read from a queue, store something away in a database or a data store of some kind. That could be Blob, that could be NoSQL. And this is a fairly typical shape and size of something that's come to be called a microservice, which is typically hosted as an indivisible part, I guess, on a cluster. You can, of course, host much bigger services where we have sort of monolithic services. And for the purposes of this presentation, they're kind of the same thing. The same challenges that we have with monolithic services, we have with microservices. So really, this is any component that we run on a cluster, which we run on a Kubernetes cluster. Let me just run the animation on this. So we have a Kubernetes cluster, and for those not that familiar with Kubernetes, we it does things like, yes, it auto scales, but it also brings an awful lot to the party as well. And what we don't want developers to do is to fight that infrastructure, or to think about traditional apps and how they might have done it in traditional apps, because invariably there's always a solution for whatever we're trying to do on Kubernetes or the orchestrator. A great example of that is log aggregation provided by the cluster, management of secrets and so on provided by the cluster, DNS and inter-service communication, being able to inject files or folders into the container, the ability to host other cluster services and have those available to our microservice or service, and also getting traffic in and out of the cluster. Kubernetes supports ingress and SSL termination, meaning that we don't need to, a lot of the things that we might traditionally do in microservices, such as run Let's Encrypt and host an SSL certificate, or do SSL termination within ASP.NET Core, those capabilities tend to now get in the way. And there are better solutions that we should use when we're actually under the control of the cluster. And if we do this, then we become a good cluster citizen, like any other service that's running on the cluster, whether that be written in .NET Core, whether that be written in Python, or even be a pre-packaged service. If we treat the service in the same way and leverage these cluster services, then it's a lot better, because if we're starting an application from scratch, we don't need to build those capabilities in. So we save development effort. And also when somebody comes to deploy that into the cluster, then it's very familiar as a good citizen of Kubernetes. A resource that we always find useful is this concept of 12-factor apps. I don't know how familiar that is to everyone here, but it's a really nice simplification of building applications. And what 12-factor talks about, it's quite a large website. I'm not planning to read it all just now, but it basically talks about the various facets of an application that we have and how those should be architected. And when we're looking at how to build a good service, then 12-factor generally has a pretty good answer for most things. So it talks about how we manage the code base, how we manage dependencies. So a good example in Netcore and NuGet packages, how we get config into our service, how we call to other services, how we build, how we deploy, and how we run those services, how we do port binding, and all the way down to how do we get stuff out of our services, not just in terms of messages that get posted to a queue, but how do we get diagnostic information out of the actual services? And obviously logs are the lifeblood of running a production system. And if we just dive into one of those examples for argument's sake, then the advice for logs is treat logs as event streams. And when we think about how we do that in a traditional .NET app, for those of you old enough, you may remember Log4Net. You may prefer Serilog, or with Netcore, you may just use Microsoft extension login. But the typical approach, and you'll see this for Azure App Service, is to write to a rolling log file. Now, when we get an app that's writing to a rolling log file, the first thing we have to do is run a sidecar container to read from that rolling log file and pump it to standard out, essentially. So when developing an app, it's always worth looking at 12-factor to say, okay, where is this going to be deployed? How should these logs be surfaced? Because when you're running in debug in Visual Studio, then the standard console output is what you use. And guess what? That's the best approach for Kubernetes as well. 12-factor says prefer streaming to standard out. And in .NET, I'm just somebody shout out. I mean, which of these libraries do you tend to use? Do you tend to use MEL or do you tend to use Serilog? Anyone?
You're using Serilog.
Serilog, great choice.
Serilog.
Serilog,
Yeah.
Perfect, wonderful, thank you. And Serilog is the best choice, in all honesty. The reason it's the best choice is if I have a very simple Kubernetes cluster here that I threw up earlier, and this by default, this is on AKS, this is on Azure, and by default, the Kubernetes cluster captures everything sent to standard out, and it dumps it in a log analytics workspace. So if we look into the log analytics workspace, and sorry, this is going to be a bit quick to load. I'll just access the workspace. Oh, that's quite slow. And I'll just look into, I'll just run the events view. So basically, straight out of the box, this is an example on Azure. They all work the same, whether that's running on AWS or running on GCP. And essentially, there is something on the cluster that is capturing the standard output of a container, and it's aggregating those logs across all the nodes in the cluster. Because when you think about logging, it's one of the toughest problems, right? Because there's a very large amount of data. We need excellent searching capabilities. And when we look at the typical output of a .NET app, then our logs are unstructured. So they're line by line format. And by default, our cluster will capture those line by line logs and we'll add a load of tags to them and we'll basically capture those logs for us. So the simplest minimum viable solution for a service is to do the simplest thing that .NET comes with, which is output into console. This is just the file new next and the weather forecast app from .NET Core 5 or .NET 5 as it's now called, not .NET Core. Apologies. And as we can see, when it slowly fires up, apologies, the reason for the prompt, I just had to install Bitdefender that was fighting furiously with Zoom and various other things just to be able to get this to run. Okay, I'm just running this under F5, which doesn't run it in Docker, of course. And whoa, eventually we get our .NET output. And there's our weather forecast app, which for any of you who've done the file new next on ASP.NET Core. So what are some of the challenges here? Well, when we think about standard plain text log format, this is actually going to generate 2 log lines. And the same if we do an exception trace from our app. When we're actually logging in plain text, we're going to get a log line for every single line of that exception. You know, good luck putting that back together and trying to work out what happened. It's pretty tricky. And this is the default with text-based logs. But unfortunately, text-based plain text logs tend to be the default for the cluster without us doing more work to output structured logs. So our answer for what to do in terms of a minimum viable microservice is write plain text to standard out and convert any carriage return line feed to just a line feed. And if we actually do that, then the actually, do you know what? I think that's actually a typo. I've just realized that is a typo. Apologies. I typed it without actually thinking earlier. So we convert carriage return line feed to carriage return, which basically gives us a new line, essentially, where we used to have, or a placeholder for a new line, but does actually return, for example, an exception trace into the single log line. So we get a single log line. And actually, Serilog has the capability to output plain text in this format. So this is a great choice from our services and is a really good way to get up and running with a minimum viable microservice outputting logs. The correct answer, again, is use Serilog, but use Serilog's compact log event formatter, which I don't know what log format you tend to use now, but Clef is a relatively standard format that doesn't have a problem with creating multiple log lines for a stack trace. It outputs structured JSON. And that's a great final format for logs. But that isn't supported necessarily by the standard cluster installs. We have to do a bit more work to install a processing package like FluentBit or FluentD in order to process these logs and then capture the various fields of the log. But as .NET developers, what we're trying to do is not fight the architecture of the cluster. So initially, we might be happy to output plain text. I'm talking about customers that are relatively new to orchestration. plain text is a good initial format, but be aware we need to do this little trick in order that our multiple lines don't generate multiple log lines. But ultimately, what we're looking to do is use clef and output standard and output structured JSON so that we don't have the problem with multiple lines generating multiple log entries. And clef is a standard compact. JSON is a standard output of Serilog. So we have a really good solution. And I still see week on week a huge number of Stack Overflow, huge number of questions on, how do we do login? And that's basically the answer. We can do this for now, and we can do this for later. And that's pretty much our login story done. And it's straight out to the 12-factor playbook as well. For any of our apps, we need to get, obviously, logs out, as we've said, but we also need to get configuration in. The advice from 12-factor is, for any configuration to pass in to a service, put it in environment variables. In a traditional .NET sense, that might be web.config, or obviously for .NET Core, which is the only real thing you can support in a container, then we're talking about appsettings.json or appsettings.release.json. And that's possible in Kubernetes, although not very pretty. So what we can actually do in Kubernetes is, as part of the definition of the Helm chart, let's see a little bit of loading. As part of the definition for the Helm chart for the container, we can actually reference a appsettings.json deployed as a Kubernetes config map. And already now we're bringing in more and more things into that. And it's suddenly, it's not looking so easy anymore. It's quite easy to use appsettings.json in Azure App Service. But as soon as we do that in a container orchestrator, we're talking about having to inject a file into the running container that can then be picked up by the service. So if we look at what the 12-factor advice is on that, environment variables, and in fact, what we should do for minimum viable service now is we can trivially add an environment variable override to our app settings, which will then mean we can use our app settings for development, and then we can override those app settings with environment variables. And it's actually very trivial to inject environment variables into a running container. Sorry, and that's a good solution. Apologies, as I said, I had a bit of a crash earlier with Bitdefender, but and what we should do later, which is the question we always get, is that's great, but how do I update my config on the fly? And the answer to that is you probably don't need to update your config on the fly, because you're giving yourself bigger problems than you might think. So say, for example, you update the config for a queue reader, and you set the queue reader from processing 4 messages concurrently to processing 16 messages concurrently. You've now got to have some mechanism in your app to either dynamically change that if it's possible, or to stop your queue reader, restart your queue reader with that new config, and then be able to inherit that config. And dynamic config is usually more hassle than it's worth. We normally find there are a small number of things that need dynamic config. And a good example of that is log levels. It's quite useful sometimes to be able to change a log level. And sometimes it's quite useful to be able to actually change dynamically the number of readers or the number of processors in real time on say something reading from blob storage, or something reading from a queue, or something processing items from a database. So if this needs to be done, I'd recommend still sticking with environment variable injection and look into accessing some key value storage at cluster level, and be able to dynamically react to those events. And the reason we advise to do this on a case-by-case basis and only for a limited number of items is because you can invariably get in the state where the config says one thing and your app is still using the existing config. So dynamically changing config is a really difficult trick to pull off, and usually it's only needed for a small number of values. But for now, go with nvar overrides, still reference the app settings, and then use netcore's allow environment override. And then later consider something like console kv, which can give a dynamic configuration. So run console kv as a cluster service, and then pull the config from console kv. So it gives you the a dashboard where you can say, actually, I want to increase the number of readers for that service, and have the service react dynamically. When we move from traditional .NET app to an ephemeral, short-lived Docker container, one of the first errors I get asked about is this little gem. Storing keys in a directory that may not be persisted, protected data will be unavailable when the container is destroyed. This is the number one question I get usually. And the problem here, of course, is that if we're running more than one ASP.NET service in traditionally called a web farm, but any form of scale out, then due to some nice capabilities of ASP.NET, like anti-forgery, that basically protects a form post by injecting a cryptographically secure challenge in the form post, we can't generate the form from one instance of ASP.NET and have it processed correctly by another instance of ASP.NET unless it has the shared key that is used to perform that encryption. And we need to find a standard place where all of the instances of ASP.NET are able to agree on that shared state. Now, obviously, the whole benefit of running in a container orchestration is to be able to have scale out, to be able to dynamically scale the number of instances of the website to handle bigger load, to be able to do rolling upgrades, to have resilience. So this is a problem that we need to solve. And the options given are the medicine's almost worse than the actual disease in many cases, because it ends up bringing in, that's the wrong link, apologies. So Microsoft's official advice on this is use a folder that's persisted beyond the container lifetime. Now, as soon as we talk about persisted storage, it scares the life out of the Kubernetes administrators, because you're then talking about provisioning the cluster volume. You need to provide that cluster volume to each instance. The instance has got to correctly marshal the use of that volume and properly give up that volume. It's never as elegant as and never as straightforward as you want. Or you can use Azure Key Vault, which is a nice solution. But one of the problems with Azure Key Vault is you need to flow into the container all of the credentials necessary to access that key under the Key Vault. So essentially, you're giving away your keys to the Azure Key Vault. Okay, you can limit permissions to that. You can restrict what permissions those credentials have. But now suddenly you've traded an ephemeral key for quite a convoluted configuration of Azure Key Vault. And Azure Key Vault, it's a pretty complicated app. Or Redis. Redis is provided by most cloud platform providers. We can run Redis as a cluster service. Redis is quite a good solution, except for the fact it's not encrypted. And then as soon as we enable Redis, we then get a warning that we need to have a key to protect that Redis data. Of course, it needs to be the same key because all instances of ASP.NET need to be able to encrypt and unencrypt that data. And suddenly we're back in a circular argument. So now we're using Redis, but we still need shared key state on disk because that key needs to be agreed upon between the various instances. This is a thorny problem. I get asked about this a lot. How do we solve this in a minimum viable way? Well, we've done quite a lot of work on this over the years, and we've actually got some NuGet packages just under final review actually before we release them more widely, because we've used this so many times on so many customer projects that we just have to publish something, because there just isn't anything out there that it solves these really tricky problems in a minimum viable way without suddenly adding so many extra services to the cluster or so many extra dependencies on our services that you get lost in sort of the extra services that just need to be deployed just to cope with this one capability of ASP.NET. And of course, nobody in their right mind is going to suggest switching off anti-forgery, which is a very valuable capability of ASP.NET and really nicely handled. So, we want to enable it, but we don't want to have to rely on Azure Key Vault and configure it correctly. We don't want to have to store keys in Redis and then have the problem of having to store, Redis is great, but the problem of the encryption key is ours again. So suddenly we're having to flow an encryption key in. So the one rather nasty hack that we have a NuGet package for is to inject a hard-coded key via config. Okay, shock horror, you might say. That's terrible, but it does solve the problem quite neatly, because we can inject the same key into all instances of ASP.NET. We can change the key, and then the key gets updated when the instances of ASP.NET are recycled. We can also protect that key in a Kubernetes secret. So it's not as horrible as it sounds, and it deals with the problem of all Docker instances, all instances of the service having access to the same key. You might be absolutely horrified by that suggestion, but it's quite a good solution as a minimum viable service just to get the anti-forgery capabilities of ASP.NET up and running. If we don't fancy that, then we can inject an encryption key. We can store that in any shared storage, for example, SQL or Redis. Unfortunately, this the storing in SQL or Redis is very, very easy. It's a single line configuration. Brilliant. The encryption and decryption of the keys is an exercise left to the reader or to the developer. And it is a horrible interface. It is the most horrible XML-based, multi-item, really convoluted interface syntax that you have to implement. We searched everywhere and continue to search for a NuGet package but we're actually just going to make ours public because nobody else seems to have put it out there as a decent implementation of this interface that works. So when you actually add this encryption, this XML encryption in, because joy of joys, it's XML, then if we have a SQL database that is used by, and it typically is SQL, that's used by the ASP.NET instances, we can store the encryption key in the database. We can store the ASP.NET DP data protection key in the database. And we can also protect that key by an injected key, because otherwise it's in plain text and it's as good as useless, really. But we can actually introduce an extra encryption. I can try and find that in a few minutes if you like, in terms of the interface, but it is incredibly nasty, and there isn't an implementation out there. So you kind of get to write your own, or don't encrypt the key. Now, we would never recommend not encrypting something as important as that. I frequently get asked, why can't we use a Kubernetes secret? Because obviously that can protect the secret. We can use role-based access, and we can stop anybody who's not authorized getting access to the secret. But of course, the Kubernetes secret is read-only inside the pod. We can make it read-write, but suddenly we open up another massive attack surface. So Kubernetes secrets are just not suitable for this particular approach. I'm hoping if you've done some Kubernetes development of any great standing, then all of this will be extremely familiar. And if you haven't yet done any Kubernetes development and you're going to do Kubernetes, you'll suddenly go, so that's what that fat guy was talking about. I've hit that problem. And now I want to cry. And just have a look for the andev packages, and we'll be putting them out there very soon. And they actually deal with all of these minimum viable solutions. With more time, I can demonstrate all of these things, but they're about 20-25 minutes each, really getting each one of these up and running, which is why I'm just overviewing them. Build and deploy. Good old .NET build, or just .NET publish these days, and it just kind of does everything, which is wonderful. So in the traditional .NET world, .NET Core, we can just do a .NET publish. That restores NuGets, builds everything. We can put extra rules in the solution file to copy across our release config and move files around. It packages it all, optionally includes a runtime, and sticks it in a directory for us. Brilliant, right? Really useful command. The 12-factor advice on this, and it's quite interesting, actually. Let me just very quickly drop into that for the build and release steps. So they nicely sort of, if you've used Azure DevOps, then it kind of works like this anyway. The build stage obviously builds the binaries, and then the release stage combines the single build once set of artifacts with config for that release and produces a release artifact, which is then deployed to an environment. And this works really well, but in the microservices world, the only option really is Helm, is invest the time to learn Helm. With the Visual Studio tools, we can automatically add a Helm template. Just literally click add Helm template. It's as easy as that. I can demo that if that will help. And then we get our Helm template directory, which is an incredibly difficult to get to grips with technology. But once it clicks, it's absolutely indispensable. And the correct thing to start with is deployments from Helm. If I just very quickly do a new, apologies, I'll just do a new project. So running at the moment. I'll just add a new ASP.NET Core. I'll call it Web Application 2. We're just doing Hello World here, so that's not going to do any harm. We'll just go with 3.1. I'll take off HTTPS because we don't generally want that for microservices, and I will enable Docker for Linux. Actually, let me not enable that for a second and then just build it up slowly. I didn't bother doing a demo like this because there's hundreds of YouTube videos out there of people doing exactly this. It's really not very interesting. But when we've got our web application, we can trivially add a Docker file, add Docker support. And obviously, before we do that, we don't have a Docker file. If we do add Docker support for Linux containers. Oh, okay. Okay, I should have, but it's been done for this one, and there's our Docker file, essentially. And then what we can also do is we can add container orchestration support, which will basically create our Helm chart. So we do Kubernetes Helm. This may work. No, it didn't. Okay, no worries. But basically, we then get our charts, web application 1, and it's basically written our Helm for us with the application name, the chart version, and more importantly, the deploy file that is going to establish our service where we can actually add in environment variables and so on. So the answer to the minimum viable, unfortunately, is yes, we need Helm. Later, the answer is we need more Helm. And this basically revolves around making our service much easier to configure using the helpers template. And this template is this template's rerun every time we access a value. But we can do things in this helpers TPL that can make our charts much, much simpler. So if we need a value that's going to be used in 3 or 4 places, we can add a processor to helpers TPL, and then we can just refer to the values once in the values file. So our story for minimum viable deploy is Helm, the Helm values file for the values that configure our service. Those values become environment variables within the Helm chart and get injected into our service. So when we actually release with Helm, we use a Helm override. And here's an example of one here. I've deployed Redis. I've deployed Redis onto the cluster. And I've got an overrides file here. And what this does is plugs into the Helm chart. Oh, sorry, it's opened off screen. It plugs into the Helm chart some values, for example, fix the maximum memory at 10 meg, and inject this password. So I can inject the same password into Redis as into the services, and then the services are able to connect to Redis and be able to do Redis type things, such as exchange keys or cache content, which we can use also in ASP.NET natively from .NET Core. We can configure it with the Redis endpoint, and it will just magically use Redis as an extremely fast cache. One of the trickier things that we need to deal with when we come into a microservices world or an orchestrated services world is the inter-service communication. So this isn't normally a consideration since we've moved away from client server and you've got your front end and your middle tier and your back end database. We've gone to this web of services that now make up a microservices based application. And I see an awful lot of solutions to this problem or to this perceived problem when one of the native capabilities of Kubernetes is DNS. So Kubernetes already has built-in DNS, and it already has automated DNS, and even protections against badly behaved DNS clients. The reason that we would not use DNS is because many resolver libraries resolve a DNS value and then never give up that IP address. So they continue to use that IP address even when the DNS has been updated to point to a new IP address. And client resolver libraries are traditionally have multiple layers of caching. So our ISP does a layer of caching. The corporate network probably does a layer of caching. The Windows desktop does a layer of caching in DNS client. Everybody caches. Not all of those are well behaved. So the reason that DNS isn't a preferred option is because traditionally DNS doesn't give up the IP address readily. The reason that there's absolutely no problem with this in Kubernetes is if I look at our, so this is our little Kubernetes cluster. We've got some pods running on there. We've got a Debian pod and an Ubuntu pod, which are just running those stock images. And we also have a Redis instance that I installed earlier. Let me quickly show you. So the Redis was deployed, surprise, surprise, with Helm. So we've created a namespace for Redis, which is a clustered shared namespace. Good place to put cluster shared services, I'd say. Then we've deployed Helm from the stable, we've deployed Redis from the stable Helm chart into the cluster shared namespace. We use the values override file we saw earlier, and we're also saying to install it if it doesn't already exist. So it's a pretty simple Helm command. We can then do Helm list, and it'll tell us what we've installed by Helm. And we can see we've got Redis in the cluster shared namespace. Now, if we had a .NET service, for example, that we needed to reference that Helm instance, then because we've put Helm in the cluster shared namespace, Kubernetes automatically has a hierarchical DNS. So if we refer to a service, say we have two .NET services that need to talk to each other, we can just refer to the other service by service name. So when we look in the cluster, the service is deployed. Let's try that again. Some network break for some reason. We can see that we installed the Redis package, but in addition to the Redis package, we get a Redis service. So this Redis service is the endpoint that we use. And if we do DNS resolution, we'll always get this IP address. And this IP address is actually long-lived. So Kubernetes does all sorts of clever things to keep this IP address long-lived. So the fact that some resolver clients hang on to the resolution of this name really isn't the problem, because the IP address is long-lived. And the IP address follows the service around the cluster. So this is a predictable IP address. So it's 10.0.13.216. So I'm within the Ubuntu pod, within the Kubernetes cluster. So I've got a shell within the Ubuntu pod. And if I do an NS lookup on my Redis instance, so say, for example, I'd injected into my .NET Core pod the address of the Redis endpoint as Redis-master, So if I do an NS lookup on Redis-master, doesn't work. No such domain. And the reason for this is that it's actually in a separate namespace. So if I was to prefix it with the namespace, then it would resolve. Good old demo gremlins. That should be. Let me just check I didn't fat finger that. That was. You're kidding me. That is a curiosity. Oh, sorry. My bad. I'm sorry. It's DNS. It's hierarchical. It's the other way around. Hence, Microsoft.com. Obviously, sorry. The higher one's on the right. Apologies. I so infrequently type this in. Yeah, of course. Sorry. So NS lookup for Redis master. I was thinking, wow, I've broken Kubernetes. That's a rare one. But anyway, I haven't. So NS lookup Redis master, because it's not in the same namespace. Because if we have a look at our services, at our pods, we can see that the Debian pod that I'm running is in the default namespace, and the Redis is in the cluster shared namespace. So we've got this hierarchical relationship between services. So we can have lots of different services. We can have a cluster shared area in a namespace, and DNS works perfectly for us, even if we have badly behaved DNS clients, because the IP address is long-lived. So the resolution of that DNS name can be cached, and it will work perfectly. So we don't need to invent another mechanism of being able to cache the instances of the service in a scale-out way. Kubernetes will handle all of that for us. So all we need to inject in to our service is the fully qualified name in terms of the cluster of our Redis instance, and our microservice will be able to contact that cluster shared version of Redis. And I think we could even connect to Redis. Apologies, Redis tools. Redis CLI. So we had Redis master dosh cluster shared, connection refused, and no doubt that is our password that we need from the Helm chart. Oh, I think it's big S for server, is it? Apologies. Easy bit configuring the host and A for the authentication key. Okay, I think I can remember that by the time I get back to the command line. Host and A for the authentication key.
Is that case sensitive? It was a capital A.
I think it is case sensitive. Darn Redis client. Apologies.
Lowercase a, isn't it?
Is it lowercase a, is it?
Yeah.
Oh,
yeah,
yeah.
You use capital A. Yeah, maybe it's that.
That's my failing memory. Apologies for that. I've forgotten what it was when I clicked off one screen to the other. Oh, there we go. So we're in. So we can set Bob to 123. Is it list keys or something? Sorry, I forget. Keys list. Oh, there we go. Okay, so pretending I know Redis, I can't think I've logged into it for about 5 years, but you get the idea. So we can connect to that Redis service, which is running as a cluster-based service. So it's quite easy to see there that we can extend our cluster-based services, make those available to our microservices, and obviously as part of the deployment, the team may deploy a blob storage-based service, may deploy a shared SQL server, for example, and possibly components like Redis and so on that are available as cluster services. So we just need to consume those from a microservice. Leading on to the last topic, I haven't got too many for tonight. The probably the other question that comes up, especially with ASP.NET Core, is that obviously we can do an awful lot in ASP.NET Core and traditionally ASP with regard to SSL. We can have a developer SSL certificate. We can enforce SSL only at the ASP .NET level. We can do all sorts of certificate management. We can even deploy a certificate with our app, deploy a password for the private key, and even establish SSL on our service. And the typical advice is to leave the SSL unwrap at the ingress and actually just have the endpoint within the cluster as HTTP only. If we're looking at very, very secure clusters, then we may do SSL unwrap at the ingress and then downstream SSL from the ingress to the service. But, to be honest, SSL session establishment is quite slow, and we can actually feel that in the latency on the first connection with services. So, worth really thinking if we need SSL protection within the cluster between services and between the ingress and the services. A better option is to deploy an encrypted network plugin, for example, or some other means of protecting the traffic between cluster nodes in flight, or even pod security policies that can actually restrict what pods can connect to what pods. So there are typically better and much more effective ways than insisting that our ASP.NET service can only be called by SSL, and that SSL has to be hosted at the ASP endpoint. Much better to protect that with lower level services, with pod security policies, and just do plain HTTP at the ASP point, and then do the SSL and wrap at the ingress, and control it that way. Initially, if we're deploying on Azure, there is an AKS native ingress that's just deployed as part of the cluster that we can use for our services. Later on, we may want to get a bit clever and we may deploy Nginx ingress. But the native out-of-the-box version with Azure does Let's Encrypt, does SSL termination, is a great way to get our service up and running. And then later on, either us as developers or the infrastructure guys can deploy Nginx ingress and get extra capabilities. I was just going to cycle back to the Helm. Oh yeah, I showed the cluster output. Yeah, I just wanted to wrap it up at that. It was really to, set the expectations of what is required as the minimum viable possible deployment for a service. As I say, because there aren't any, as there aren't any, not never mind any good packages, there aren't any packages out there that do a lot of this standard capability, especially around data protection. Then we're just making those open source, and we're actually releasing them in the next few weeks. So there will be sort of very standard pluggable ways of implementing these things without having to implement it from the ground up. If anybody's had any experience of those interfaces, I'd be interested to hear it, but they are pretty horrible and pretty tough to get a good coverage of unit tests to get them working effectively, because they bring in, believe it or not, the two different XML libraries in .NET, which is horrific. So the two separate, not intercompatible XML libraries both are used in the interface implementation, which is pretty terrifying, really.